Hello, Calc kids. We're letting go of chapter 8, and here we are on unit 7. So yeah, we're backtracking, and we're going to pick up these few sections. As you can see, there's only about 5 sections listed here for unit 7, and that will complete all the Calc AB topics that we need to cover for the exam. We will be doing this one Friday. These will be done together on Monday. And then this is also done together. This will be at least a Tuesday, Wednesday scenario, and then or a two-day teach on that, because that's an important topic. And then hopefully we'll have probably 2 days of review and then a test. So we will wrap this one up in about probably 6 days or so. So 7.1 is nice intro unit. It talks about differential equations and modeling these differential equations. One of the important topics for calculus is these are differential equations. A differential equation involves, the variable x, y, and then the derivatives of x and y perhaps. Well, the derivatives of y, but with respect to x. And we could definitely use other variable names, so there will be these derivatives sitting inside our equation. When we get to a solution of a differential equation, that's a function that satisfies the differential equation when the function and its derivatives are substituted into the equation. We are probably not going to do a lot with that. That really is section 7.2, but I'm going to go ahead and just kind of pass on that. We've talked about general solutions, so we have done a little bit of this work in Unit 6, where we worked with general solutions to these derivative equations. And then we've also had a singular solution, or what we refer to as a specific solution or a particular solution. So you're going to see some of the same stuff again that we have done earlier. We'll just get it a little bit more ramped up in this unit. It'll be a little more difficult. So when I'm looking at this box here and it talks about examples of differential equations, why would these be considered examples? Well, I notice I'm seeing derivatives. I'm seeing a y variable. Second derivative plus a first derivative equals the original equation. And when this talked about a solution to the differential equation, it satisfies the differential equation when the function and its derivatives are substituted in. So if I had been given f of x, I could generate f prime of x, and I could generate f double prime of x, and I could, substitute all of that stuff appropriately into the correct spot and see if I indeed have an equality happening. So that is what we're kind of referring to. And here's just another example of a differential equation. Moving on. Today we're going to take word problems like example 1. Let's just read it and then I'll come back to the box. It says example 1, a particle moves along a straight line. Its velocity v is inversely proportional to the square of the distance s it has traveled. Which equation describes the relationship? And we're looking at a multiple choice question here. Well, this wording here, let me get a highlighter going. Its velocity is inversely proportional to the square of the distance s. I need to try and write an equation about that. And thinking back into previous math classes, we've had things where we talked about direct proportionality and inverse proportionality. With the direct, most often it'll just say it's proportional to, and that means it's directly proportional to. So if A is proportional to B, then I could say A is equal to some constant of proportionality times B. That's how we would structure that one. Inversely proportional, sometimes we say proportional to the reciprocal. If A is inversely proportional to B, then A equals, still have to have that constant of proportionality K over B. There's that reciprocal idea. Instead of B, we're going to have 1 over B, where K is the constant. So coming down into example 1, velocity. Velocity is inversely proportional to the square. I don't know what they want to use for velocity. I'm thinking maybe they want us to use v. to the square of the distance. So there was that inversely, so I know it's going to be a k on top, and underneath is where my variable is going to be, and proportional to the square of s. So I'm loving B. It wouldn't be dv dt, because if I went to dv dt, then we're talking acceleration, aren't we? Yeah. So that's why I could rule out, definitely ruling out C and D. And then, well, the first one, it does have the velocity, it does have the constant of proportionality, but it's talking about time squared, where this one talked about S being squared. Number 2, a puppy gains weight. Oh, look at a cute puppy. A puppy gains weight W at a rate approximately inversely proportional to its age T in month. Write an equation that describes this relationship. So the weight, whoops, it's not doing what I wanted it to do. The weight W at a rate inversely proportional to the age T. So we've got variables to work with, and it talks about the rate of W. So how do I get to a rate? Well, little calculus gets us there, doesn't it? The notation dW dt, the derivative of weight with respect to time, is equal to another inversely proportional. So K would belong on top, and it talked about proportional to age, where T was in months. That's pretty easy. I can do that. You can do that. Number 3, Mr. Cortez is swimming in a straight line across a lake. His position from the starting position is given by P of T. P for position maybe? Where T is measured in minutes since the start of his swim time. During the first 30 seconds, Mr. Cortez's acceleration is proportional to the cube root of the time since he started his swim. So basically T there. Write a differential equation that describes this relationship. So I'm just going to list out things that we learned as we read this. P stood for the position function, didn't it? P of T. T is our independent variable. I know that because it's inside the function notation. T is time. Time was measured in seconds. And then, oh, I'm sorry, measured in minutes. I read over here 30 seconds, but then I came back here and saw this. How about minutes? And what else do we know? We want, so the true sentence that I'm trying to represent, acceleration is proportional to the cube root of his time since the start of his swim, where T would have been 0. Acceleration, I want acceleration proportional. Can I get to acceleration if I have position? You know the answer to that. Why, of course we can. So if I took one derivative, or I could write it as dp dt, and I think for differential equations, I'm going to write it the dp dt style, and that gets us to velocity. So I'm still not at acceleration, and then we know, oh, take one more derivative. So if I went to p double prime, or how do we write out second derivatives? Just like this. And that will be our acceleration, won't it? That'll represent acceleration. So now I know what my notation style is going to be. I can do the left side of my equation. The left side of the equation is going to be d squared p over dt squared. Save a little room because we actually have more work to do once we get this written out. So I've got d squared p over dt squared is proportional to the cube root of time. Proportional means just direct proportionality, so k times cube root of time. Okay, so I wouldn't need the parentheses, but it looks pretty. Now, it says write a differential equation that describes this amount. Ooh, can I do that? I don't think so. I don't think I have enough information. We've got the 30 seconds, but yeah, I don't have anything to plug in for perhaps here and here so that I could solve K. So I guess this is an unsolvable one. I lied. We're done here. There's our answer. It's the next one we can actually find the K value. So then, for example, 4, leave a little space as we write this out. The force of a spring, the force, capital F, of a spring on a trampoline can be related to the distance, capital D, it is stretched. The rate of change of the quantity of F, the rate of change of the quantity F with respect to the distance D is inversely proportional to the natural logarithm of the distance D. That's a lot. If the rate of change of F is 3 units per centimeter, then the spring has been stretched 0.2. That would be distance, wouldn't it? What is the differential equation? So for this one, we actually are going to be able to solve for K. So there'll be a couple steps for us. First, let's just focus on getting that differential equation written. The rate of change of the quantity F. F was equal to force, wasn't it? And then if I did dF, d what? Well, it talked about with respect to the distance d. So that tells me on the bottom, I want small d, big D. The differential of d is the rate of change of force. Rate of change of force is what that would represent, wouldn't it? And d equals the stretched distance of the spring. Okay, so we know what our variables represent. Let's go back and write this equation. The rate of change of the quantity F with respect to distance D. That sounds like a dF dd is equal to, because I saw an is, there's our equals, inversely proportional K over something, inversely proportional to the natural log ln of the distance D. Boom. Now, there's just the general equation, but this time, since we know dF dd is equal to 3 units per centimeter, and that occurs, then the spring has been stretched. Then we know D, the stretch distance of the spring, is 0.2 centimeters. So we're going to substitute into our differential equation. Often, I guess I don't need the dash, just diff EQ for differential equation. Now, let's substitute. 3 goes into the FDD, K, and then it is over a 0.2, which means K is equal to 3 times 0.02, or we found our constant of proportionality by multiplying those. And, oh, doggone it, natural log. There we go. Woo! Missed that. But the fact that we have a natural log going on. How did I miss that? 3 will be 3 times natural log of 0.2. Well, that would be a very exact answer. I have it in a rounded form. My rounded form is, I had negative 4.828 as found on the calculator. And now, final step is just a rewrite. So I need to be able to see my original function, and now I want to rewrite final form of that differential equation. And it's going to look like dF dd is equal to our K value of negative 4.828 divided by natural log of the spring stretched. Okay, so if I knew D, how far we stretched it, I can come up with the rate of change of force. So you will have to do a few of those on homework. Last question. A chemical is diluted out of a tank by pumping pure water into the tank and pumping the existing solution out of it. So the volume at any time t is 20 plus 2t. The amount of Z chemicals in the tank decreases at a rate proportional to Z and inversely proportional to the volume of the solution in the tank. Which equation describes? So we know that Z, which is the amount of chemicals. And we also had this is what I was looking for, the volume in the tank, volume in tank. So we're trying to write, where's the sentence that leads us into our setup? Would look something like this. The amount Z of the chemical in the tank decreases at a rate. Okay, so decreases at a rate. Z decreases at a rate. So how about a dz dt is equal to proportional to Z, so a kz, but inversely, yeah, we can mix these together, can't we? But inversely proportional to the volume of the solution in the tank. Ooh, this was also equal to 20 plus 2t, wasn't it? So 20 plus 2t, just because I started looking at the answers given. And maybe my putting v in here was just me, assigning a variable because that's what my brain did. But really that 20 plus 2t represents the volume in the tank. I think this is our setup. Does that match? It does indeed. It matches to A. That is what homework's like today. It's going to be a beautiful thing, won't it? So you have homework worksheet 1 through 12. And first page, just writing out those equations. If you're given enough information, you will be expected to actually solve out and find K. And perhaps I should tell you which ones that pertains to. Hang on a minute. There are 4 questions that have you take it that extra step. So why don't you put a star or circle 5. This one will be finding K as well. So you'll write the equation and find K. And number 7 as well. So 5 and 7, you can go the extra step of finding K because they give you extra information. Anytime you're getting this extra information, you can be a little bit more specific about the differential equation. And then number 9, I found it, and number 10. So 5, 7, 9, and 10, go ahead and find K and find K. That should be good. All right, not too hard of assignment today. A nice intro to the section, to the unit 7, differential equations, slope fields, all good stuff. See ya tomorrow.